simultaneous screen operation, and I'm not going to try to butcher his name, so I'll let him introduce himself.
Hello, everyone. My name is Uri. Hard to say. So I'm a Sora. It's very simple. Okay, good morning, everyone. I'm Sora from the University of Electrocommunications, Japan. Today I'm going to speak about the new high-density tactile presentation method for the smartphone. Okay. So nowadays, many people use smartphone in their daily life. Touchscreens have greatly improved the way we interact with devices and making them easier to use. But they come with the price. The spread of mobile touchscreen devices, improving comfort and accuracy become an important issue. For example, the one problem is the lack of the clear tactile feedback. It causes a host of problems, such as accuracy and safety problems. First of all, I introduced you some previous research that's achieved to provide the tactile feedback for the smartphone. Most of them were presented the tactile feedback to the finger that is touching the screen. For example, active click realized the click feeling by vibrating the entire screen. And the Tesla Touch created a texture feeling by controlling the friction on the screen. While this device has some success, they are limited in spatial resolution with the present vibrations or rough shapes. The main issue with this method is the tactile display must not obscure the screen. This dramatically limits the ways that stimulation can be presented. So to cope with this issue, some studies propose the method that the stimulation be presented to the back of the screen. Same field used vibration motors and palm touch panel used electro-tactile display to present the tactile stimulation to the back area of the smartphone. This method presents the tactile feedback to the entire palm of the hand that's holding the device. However, when we use the smartphone, in a traditional smartphone interaction, we don't usually be touched with the smartphone with the entire palm of the hand, like this. We don't use like this. Okay. Then, considering all these issues, we proposed a new method. In our system, the tactile stimulation is presented to a single finger on the back. The information around the finger is delivered to the finger on the back as a tactile stimulation. For this reason, we have three merits in our system. The first is the spatial resolution of the fingertips high, and we thought the presentation to the finger is more appreciated than presentation to the palm of the hand, because the shapes on the screens are touched by only one fingertip. The second is that the device becomes small and simple and low cost. And the last is we do not have to change the way we interact with the smartphones because its size small. Okay. There is a system algorithm. As I mentioned before, in our system, the information around the operating finger is present to the finger on the back. The tactile pattern corresponds to the shape displayed on the screen and the operating finger. In other words, the tactile pattern follows the movement of the operating finger, and user can perceive the shapes tactilely with their presentation finger on the back. The screen image is image and tactile image were image of the mirror image of each other because the tactile display faces in opposite direction from the touch screen. As you can see in the video, the operating finger moves on the touch screen. The finger on the back feels that the movement. Okay, here's the. Okay, next we show in this slide the schematic of our hardware prototype. We use the smartphone and electro-tactile display with 61 electrodes. The tactile display size is small as a fingertip size, and it's developed in our laboratory. We use the USB cable to connect these devices. Okay. Then next we conducted two experiments. to evaluate our device, the first experiment is a line direction recognition. We conducted this experiment to note that the confusion doesn't occur between the different angles and mirror image because the tactile image is on the back of the smartphone. The second experiment is the shape recognition. This experiment was to validate the ability to identify more complex shapes. And we conducted each experiment in 4 conditions for different interaction types. Uses the device with one hand or both a hand, and holding the device with right hand or left hand. Okay. The experiment 1. Here's the experiment design. The 4 types, 5 repetitions, and 4 conditions, 8 participants. There were a total 640 trials. The participants did practice about 2 minutes prior to the experiment. During the experiment, shapes were not shown in the screen, and as we can see, the video is showing the experiment procedure. Okay. And then we measured the response accuracy and recognition time. The result is shown in here. The left is the recognition rate, and the right is the recognition time. X-axis shows the line types, and Y-axis shows the performance. Overall, the recognition rate and recognition time speed were high, and no confusion was found between the mirror image. And interestingly, in our result, we found that using one hand is more accurate and faster than using 2 hands when they use our device. We thought it is because the behavior of touching and feeling with one hand is more natural in people, maybe, and it's because of the orientation of the fingers. And although there were no difference found between the device holding hands, which is left or right. Okay. Okay, next is experiment 2. The experiment design was almost same as the experiment 1, except the shapes and participants were a little bit changed. Shapes were square, round, triangle, and the cross shape. 5 out of 8 participants were conducted the experiment 2 days before. Here we shows the experiment result. Experiment 2's result. Performance were high, and the recognition rate of one hand was marginally higher than 2 hands. So that's using one hand was still better than using 2 hands. However, recognition time and time of the one hand and 2 hand was almost same. Also, as we can say, although the shapes become more complex, mean recognition time has got faster than the experiment 1. It may be the participants who conducted experiment 1 will get used to our system when they do experiment 2. Okay, finally, we made some applications to demonstrate our device. You can try our device in interactivity number 26. We'll be waiting for you. Okay. Now, conclusion is we made a high-density tactile feedback method and we conducted the experiment and we find that user could stably distinguish the shapes, and performance of one-hand interaction was high. And in the future, we are planning to develop applications for the visual impairments. Okay, thanks.